Hello, welcome to this clip having a look at calculating the Ka value of a buffer in a partial neutralization. So let's have a look at why exactly it's a partial neutralization. To do this, we've got to work out the individual moles that we have of each component to start with. So we have a strong alkali and we have a weak acid. So for a partial neutralization, we need to make sure that there's less moles of the strong alkali compared to the moles of butanoic acid. So working them both out, slightly different bits of data. We've got mass for the potassium hydroxide and we've got volume and concentration for the weak acid. So the key thing here is that the number of moles of OH- ions is less than the number of moles of weak acid. So it's a partial neutralization, which leads us to use the ICE method. So the ICE method is basically taking our dissociation of the weak acid and working out the initial moles, change in moles once it reacts, and the moles left at equilibrium. So taking our 0.094 moles of weak acid, obviously at the beginning it hasn't started dissociating yet, so there's no moles of butanoate and no moles of H+. So what happens if you add the KOH to that? It reacts with an equal amount of the weak acid, so you subtract 0.0604 from 0.094. You will also get some of the conjugate base. This is the ethanoate ion produced, and you'll also get some H+ produced, but that's reacting with the OH-. The whole point is that the H+ is being removed from this system by reacting with OH-, and this forces the position of equilibrium to move to the right. So we're left with 0.0336 moles of our weak acid once all of the potassium hydroxide has been used up, and we've also made 0.0604 moles of our conjugate base, the butanoate ion. So like we said, the KOH will neutralize an equal quantity of the weak acid. So now we can start using the Ka expression and inserting the values that we have. So to work out the moles of hydrogen ions, we need to do 10 to the minus pH, which gives us 8.511 times 10 to the minus 6. So therefore we can multiply that by 0.0604, but dividing that number of moles by the volume. Now the volume has to be converted to decimeters cubed, hence why it's 0.25. And a similar calculation occurs on the denominator. So now we can put those into a calculator, which gives us 1.53 times 10 to the minus 5 moles per decimeter cubed. Okay, hopefully this has been a useful look at this question, and thanks for listening. Until next time, see you soon.